So what happened to a black hole? It forms, and then what? Is this black hole exploding back in our universe? Or is it possible that something has happened? Namely, is it possible that these black holes divide itself from our universe and creates a new region, namely a new universe?
According to most loop researchers, matter that falls into a black hole will eventually bounce back out, forming its time reverse, a white hole. Just as nothing can escape a black hole, nothing can get into a white hole. Black holes bouncing into white holes could be linked to fast radio bursts, energetic signals astronomers have recently discovered that have been dubbed the biggest mystery in astronomy. But an alternative is that white holes quantum tunnel into another distant region of space-time, or maybe even into a new universe with different values for the constants of nature.
So there are two scenarios which are inequivalent and they are competing. And now we have to understand better. I mean, one thing is observations. So either we observe the first scenario, which is observable, or if we don't observe it, then we always have the second one, which is not observable. but we also have other theoretical considerations, tests. We can check how those scenarios are consistent with other areas of physics, with other phenomena.
Black hole evolves by evaporating, by getting smaller and smaller, by letting off these particles that are known as Hawking particles or Hawking quanta. And there was a question when we first came up with the idea that black holes might transform into white holes. There was a question of whether this might happen early in their lives or quite late. And our most recent thinking is that it actually happens deep into the lifetime of the black hole. So the black hole mostly evaporates via these Hawking quanta, and then it reaches a very, very small size, what we call the Planck mass, which is about the mass of a hair, a human hair. And it's only once it's reached this size that it transforms. So this leads to this incredible timescale that I've never seen anything like elsewhere in physics, much, much longer than the age of the universe. Let's see, 55 orders of magnitude larger than the age of the universe. It's quite an extraordinary timescale.
I don't think it's resolved yet, but the calculation seems to favor a longer time. Technically, m cubed, where m is the mass of the initial black hole, rather than m squared, so which is a much longer time. M squared would mean that the black hole can explode when it's still big and macroscopic. M cube would mean that the black hole has to become very small, evaporate to be small before tunneling into a white hole. There are calculations to be done. The problem is that calculations have been done, but in very crude approximations. So the question is, are these reliable, or by doing a better approximation we understand better? I don't know. I'm not sure yet. But the weight seems to go toward a long life. Long life means less plausible the idea that they're connected to fast radio bursts. Still there, but it's less plausible. And more plausible the connection to dark matter.
Physicists don't know what makes up a huge percentage of the matter of the universe. So this is the famous problem of dark matter. And there are two indications that there's something interesting with black holes and dark matter. So if many black holes were created in the very early universe and they evaporated down to these very small black holes, then you could have these small black holes making up a bunch of matter, and they wouldn't interact with anything, and we wouldn't know that they were present necessarily. And so this could be one candidate dark matter. So that would be another experimental avenue to try to look for signatures of these old black holes. LIGO, the Gravitational Wave Observatory, and Virgo and the other observatories are starting to measure gravitational waves, and they're finding black holes that are like 10 solar masses and 30 solar masses in this range. And so there are many, many more of these kinds of this type of black holes than we expected, and they also might make up some portion of dark matter. So it may be that the picture that's emerging of dark matter is much more complicated, that it's made up of multiple different kinds of things, and that those things are just becoming visible to us now.
One of the beautiful novelty in this conference, it's a prediction by Eugenio Bianchi and Hal Haggard, which is very simple. If the black holes were formed in some thermal ensemble in primordial fluctuations, they are likely to be formed according to a distribution which has to do with the Bekenstein-Rosen entropy.
Since the 70s, it's been recognized that black holes have this remarkable entropy, a very, very high entropy. So this is called the Bekenstein-Hawking entropy. And this entropy has a really beautiful property, which is that it's closely related to the surface area of the black hole.
The way we understand black holes is that they are not simple objects, they are not simple solutions of general relativity, they are really complex objects that have a temperature, they are hot, they have an entropy, and they consist of an immense, humongous number of states. And one can ask, what are their statistical properties and what can we predict for their typical behavior?
A very interesting aspect of it is that when you spin a black hole, the entropy actually decreases. There are fewer allowed configurations for the microstructure of the black hole. What would happen, what would be the case if a black hole was formed in thermal equilibrium? So if you had a bath of temperature all around, what you would expect is that every possible configuration of the black hole would be equally likely, and so you should form the black holes that have the most possible configurations. And it turns out that the black holes that have the most possible configurations would be black holes that have zero spin.
So then the non-trivial question is, when is it that these black holes are in equilibrium? In an equilibrium that would allow you to find the most likely configuration. And one possibility is that black holes produced in the early universe, primordial black holes, these might be in equilibrium, especially the ones that are formed in one of the phases where the pressure drops, the probability of producing them is enhanced, and the matter that produced them was already in thermal equilibrium. Black holes produced in that phase would have a mass that is accessible to present experiments like LIGO and Virgo, mass of 20-25 solar masses. And if they are in equilibrium, they would have a small spin.
Now, when a star collapses, star spins, so becomes smaller, spins faster and faster and faster, so it produces a black hole which spins very fast. So black hole produced by stars are spinning fast, but primordial black holes are probably not spinning.
This prediction wasn't recognized before, and we've started to build it out and try to understand what comes out of it. And there's a compelling connection with the gravitational wave measurements that are happening right now. So at LIGO and Virgo, they're detecting pairs of black holes that are rotating around one another and crashing into each other. And they can't yet measure the individual spins of the black holes very effectively. But they can measure a kind of combination of the two spins. And so far, the measurements are consistent with each of the individual black holes having zero spin. And so this connection between black hole entropy, predicting that you would expect black holes that were formed in the early universe in thermal equilibrium to have zero spin, and the fact that the LIGO is measuring black holes that are consistent with zero spin is really compelling to us. There's this exciting moment now where they are starting to make measurements of black holes on a weekly basis. So you can even check the GRACE database, and they show you every day what they've measured at LIGO. They don't release the numbers yet, but they're coming. And so we're starting to have a picture of a whole population of black holes. And since this prediction of zero spin for the black holes is a statistical prediction, it's about a population of black holes, there's the possibility to really test it through these LIGO measurements. If you'd asked me 5 years ago that we were this close to being able to check a prediction of quantum gravity, I would have been surprised. And I'm really excited about the possibility that this would be happening in the next few years. So this is just a mechanism. If black holes can be formed in thermal equilibrium, it's a mechanism to form them with zero spin. And you might think of another mechanism. You might think that there was a star that had some spin, it formed a black hole that had some spin, but then it was sucking on matter in such a way that it spinned it down, it got to very low spin. So one might think of other mechanisms. So zero spin black holes on their own is not enough to say we've tested quantum gravity. But if we can start to connect different sets of ideas, so if we could start to show that these black holes were formed in the early universe and that they have zero spin, you start to make connections between the various parts of the ideas, then I think it would be a much more a test of quantum gravity.
If these results are confirmed, would they tell us which theory of quantum gravity is correct?
One of the remarkable things about black hole entropy is that so far it seems to be independent of your favorite theory of quantum gravity. The Bekenstein-Hawking entropy has been derived in loop quantum gravity and string theory and in numerous approaches. It seems to be a very robust feature of quantum gravity. But it would tell you that black holes have a statistical nature. They have a microstructure. So, so even if it wouldn't select one theory for you, it would be big progress.
Black holes seem to destroy information that falls into them. But quantum mechanics says that information can never be destroyed. How to resolve this paradox may give us clues that will help to distinguish between competing theories.
String theory, the belief is that information goes very, very slowly through very tiny corrections out of the horizon. While we believe that for answering this question, it is essential to explain what happens with information that we think, and classical physics, semi-classical physics shows, falls directly into the singularity.
Another great idea, which is tantalizing, is related to dark matter again. It could be not just black holes produced in the early universe, but black holes from a previous universe that went through the bounce. Something Francesca Vidotto has been pushing, and it's plausible. Of course, it demands one has to believe the bounce, one has to believe this transition, so there are many things which are not confirmed, but these are all things which are more and more plausible, I would say, today.
If there is a pre-Big Bang phase in a bouncing cosmology in which the universe would have undergone a contraction before the current expansion, well, in this contracting phase, a lot of black holes could have formed, and they could have been in the remnant phase. And according to what also other scientists are studying, for instance, Bernard Carr or Robert Brandenberger, so it's possible for those pre-Big Bang black holes to pass through the bounce and be present today. What I find very interesting is that in this case, these black holes in the contracting phase provides exactly the right kind of matter for the universe to give the right power spectrum later, at a later time. So this happens without the need for inflation. So there is a coherent scenario in which primordial black holes are there, and not only they are there in order to provide dark matter, but they also provide the right source for getting rid of inflation.
For the moment, the effort is to see whether this scenario is consistent with standard cosmology, where all the energy balances go through cosmology. Direct observation of these small white holes, they're very little. They interact only gravitationally. They're dark. They're dark matter. That's exactly what they are. So how do we see them? So for the moment, the weight is, this is the only explanation of dark matter that actually does not require new physics, just general relativity and quantum mechanics. So that would make the plausibility. A direct observation, people are squeezing their head, but I haven't seen anything credible yet.
At the moment, I think all of us want to see quantum gravity before we're too worried about distinguishing theories. It's not that we have a menu of 1,000 theories that we have to distinguish. It's actually we have very few consistent theories, and it would be just wonderful to see that gravity is quantum mechanical.